Hi, my name is Doug Black. I'm managing editor of Enterprise Tech, and we are today speaking with Karl Freund, who is senior analyst, machine learning and HPC at the analyst group Moor Insights. And Karl, we were chatting earlier about this kind of interesting dichotomy that exists between the mission of the conference and the conference agenda and the emphasis and focus of most of the sessions over against the marketing strategy of a lot of the exhibitors. The conference is putting less emphasis on HPC in the enterprise and in industrial commercial sectors. Whereas a lot of the vendors are putting more emphasis on that.
Yeah.
So I know you had some thoughts about that.
You know, like so many other things, you have to follow the money, okay? And when the governments are spending a lot of money, the large supercomputer centers, national labs, both here in the U.S. and abroad, they have a lot of money to spend. And so they do, and they buy a lot of computer hardware, hire a lot of people. And historically, that's been the case. The industrial market for HPC is much larger than the top 500, and there's a lot of excitement in that market around the uses of HPC in a variety of disciplines, whether it's material sciences or computational fluid dynamics. But the interesting thing is how the cloud sort of learned from HPC. How do you build, effectively a supercomputer with 1 million or more computers to be able to respond to a Google search? And the cloud learned a lot from HPC, and now it's the other way around. Now the HPC is learning a lot from large cloud vendors and social media companies, social networking companies, because they're applying machine learning to solve problems that do not lend themselves well to traditional, digital numerical analysis kinds of techniques. And so HPC is now adopting machine learning to solve problems that are really not solvable using traditional techniques. So it's a bit of a virtuous cycle, and these things will ebb and flow.
So there might be this dichotomy, but it's very complementary as well.
I think so. Yeah. I think it's healthy.
Yeah, very good. So just in your days here at the conference, what's really excited you or caught your interest?
It's like what didn't excite me at this conference. There was so much going on. I've been coming to supercomputing shows since a long time ago, since I had hair, and that was a long time ago, back in the 80s and 90s. And this year there were three areas that excited me. I would say it's silicon, systems, and science. On the silicon front, this was a very busy year. We had good news and bad news. The disappointing news is Intel canceled Knights Hill, which is a big blow to quite a few supercomputer procurements that are ranging in the hundreds of millions of dollars of contracts that all have to be rewritten now. On the positive side, there's some things that we've been waiting a long time for that are finally happening. ARM has finally shown up with a very credible platform, thanks to Cavium Thunder X2, which has not only shown up with really good performance numbers and a rich suite of software from ARM Alenia Studio, as well as Red Hat, but now Cray and HP have joined in and stepped up to the plate. Both Cray and HP introduced readily available systems, servers, designed specifically for this ARM platform. I worked in the ARM business for a while, and it's great to see it actually come to fruition. You asked me earlier, so what's so special about ARM? I think it's the design flexibility it gives to customers and silicon manufacturers. So Cavium is really good. Simon McIntosh Smith out of the UK has run some benchmarks showing Cavium is Xeon class or better. And it's not that ARM is inherently a more efficient architecture. It's they chose a system design with more memory bandwidth and more I/O bandwidth and more I/O memory capacity per core that allows you to get more efficiency out of the total system. So that was interesting. AMD showed up with EPYC, with new floating point benchmarks that show that AMD EPYC x86, but still a different system design with more memory bandwidth and more I/O bandwidth, triple the performance per dollar for floating point operations compared to a top-of-the-line Intel Xeon SKU. So very, very impressive. And finally, you can't have a conversation today about HPC without talking about GPUs. And NVIDIA, while they did not bring out new silicon, their silicon they did bring out last April, the Volta GPU, is now shipping in full volume production. It's available worldwide in every major cloud property. So whatever cloud vendor you're using, they now have Volta GPUs available for rent. And NVIDIA took a step further by making their GPU cloud available with HPC stacks. So you take a container and you build a NAMD stack, all fully rationalized in terms of versions of libraries and compilers and everything else, and operating systems, and build a container. Click, click, click. You download the container on your favorite cloud or on your own hardware, and you're off and running. So it really makes the GPU hardware much more accessible. You don't have to spend days or weeks procuring and configuring software and hardware stacks before you even get to start to work on your science. You can just click and go. So it's not just the hardware that was exciting there, it was a silicon side. On the system side, all three major vendors, HPE, Lenovo, and Dell, all announced fairly bold strategies for both HPC and machine learning. So they're all doubling down on HPC. They're all doubling down on machine learning. And they're all three bringing out new products designed for machine learning's highly scalable platforms with lots of GPUs. On the science side, two things caught my attention. One was quantum computing. D-Wave announced their 2,000 qubit platform, which is getting a lot of interest and a lot of good experimentation in national labs as well as in industry. I was talking to Bo Ewald, their CEO, this morning. He told me that they've got a company that's actually built a test of advertising targeting on the D-Wave quantum computer with dramatically better results than they can get on traditional computers. Now, quantum computing is not ready for prime time. And I think we're still, maybe 3 to 5, maybe even more years away before you'll see these running production workloads. And they won't run every production workload. There's a class of problems that they're ideally suited for. So that's one thing, quantum computing. But the other thing really, as I mentioned earlier, is just the infusion, the intersection of high performance computing and machine learning. There are problems that you cannot solve. Not only can you not solve them today, you can't solve them with exascale. There are problems that someone described a problem to me today. He said, if you could take every grain of sand on the planet Earth and turn it into a digital computer, and if you could figure out how to write software to parallelize across those trillions and trillions of cores, it would still take millions of years to solve some problems.
What would that be? What would be the
Problems that just don't lend themselves well to modeling through normal laws of physics and the numerical analysis that simulates those normal laws of physics. So these are problems with relatively speaking, an infinite number of variables. And in some cases, machine learning combined with quantum computing, interestingly enough, may be ways for us to solve problems that otherwise would never be solved with normal digital computing techniques.
Yeah. Well, yesterday we spoke with England Go of HPE, and he talked about this tremendous potential power, or actual existing power, of combining HPC with machine learning.
It's truly amazing. We're seeing results, for example, in quantum chemistry. Quantum chemistry is sort of the long pole in the tent when it comes to getting a new drug to market. So it takes 20 years to get a new drug to market between the technical hurdles and the regulatory hurdles. With machine learning, we've seen results that could be 1,000 to 10,000 times faster than using fastest supercomputer you can put your hands on. And part of this is because it's a different approach. You're not trying to calculate the answer, you're trying to estimate the answer by going through reams and reams of data, training a machine to recognize the patterns in those data sets, and then giving it a new data sample and say, if I ran the simulation on this, which might take me 3 months to run, if I ran the simulation, what would the answer be? Let the machine tell you what the answer would be. Now, it's not an exact science. It's a probability distribution of the correctness of that answer. And machines are getting to the point where, you know, for a lot of problems like facial recognition, we're at an excess of 95% accuracy today. The human brain is about a 95% accuracy at recognizing faces. And so they're already better than humans at that.
If
and
you
of course,
had the
self-driving
name,
cars,
connecting names to faces, it's much lower, I'm sure.
yes, connecting names to faces humans are really bad at. From personal experience, I can tell you. You know, but for things like self-driving cars, you have to have 99.9999% accuracy, because if you don't, then the automobile manufacturer is liable for the accident. At least that's the law in Germany, and may soon be the law elsewhere.
We heard talk of this.
And so machine learning's got a long way to go, but what we're already seeing is having tremendous impact on science and society.
Very good. All right, Karl. Well, thanks so much for your time.
My pleasure.
We've
My
enjoyed
pleasure.
talking to you. And we'll see you next year at SC 2018.